Hello, I'm Alex Howe, and this is the Science Meets Fiction Exoplanets Review for June of 2022. And of course, if you've been paying attention, the big news right now is the James Webb Space Telescope is now fully armed and operational, and taking pictures of the universe, including spectra of exoplanets. But that's a July story, so you'll hear about that in the next review. Right now, we're talking about the new exoplanets papers from June. And when I was making the slides, I noticed I ended up writing out the explanations for the science more than in the previous reviews. I'm not sure if that's the way I want to go about it, so let me know in the comments if you like it or don't like it. And we'll start out with the notable new exoplanets discoveries in June. And we have a pair of planets from TESS orbiting red dwarf stars, TOI 4479b and TOI 2081b. And like many of the notable planets from TESS, because it mainly looks at short period planets, these are red dwarf planets, kind of like this illustration. And the paper is specifically about color validation, which I actually wasn't familiar with. I wasn't up on the latest detection and verification methods, but it's a pretty clever method. The issue with TESS is that in order to get accurate light levels, it actually has very large pixels. Pixels that will cover several or even many background stars. And it's slightly out of focus. And it does this to spread the starlight over several pixels so you can get better statistics on it, because then you have multiple measurements of the starlight. And you can still tell which star the light came from by looking at the balance of light across the different pixels. And color validation is related to that. It looks at how the different colors of light changed in the balance of pixels around the stars during the transit. And if different colors change by different amounts or in different ways, that indicates that it came from the star in question and not from a background star that's a different color. In any case, both of these planets orbit red dwarfs. Both of them are sub-Neptunes. TOI 2081b could be a super-Earth that's based on the margin of error in the radius. It's not exactly 2.04. But it's probably a sub-Neptune with a thick atmosphere. And both of them are hotter than Earth. Earth's average temperature is 288 Kelvin. And for these two planets, the one is 500 Kelvin and the other is well over 800. But the most interesting thing is that one of these planets, TOI 4479b, is in what we call the Neptune Desert. And the Neptune Desert is this region close to the star where we find very few Neptune-sized planets, because we're not entirely sure either formation processes or photoevaporation of the atmosphere make it difficult for planets to hold on to a hydrogen atmosphere unless they're very big, Jupiter-sized. And you can see that in the classic radius period diagram. TOI 4479b is the green star, and you can see it falls into the Neptune Desert. It has a larger radius than you would expect for a planet orbiting that close to its star. Now, it's kind of on the edge of the Neptune Desert. The lines drawn here, I'm not sure exactly what's going on. I suspect those are the lines for a solar-type star, and around low-mass stars, the Neptune Desert is shifted closer. So this planet's probably closer to the edge than it looks, but it's still right on the edge, so it's an interesting case study for planets that don't quite fit the usual patterns. Of course, we've been finding things that don't quite fit the usual patterns for 30 years now, but that only promises more interesting finds to come. Next up, we have a paper looking at the population of exoplanets as a whole, constraining the planet occurrence rate around halo stars of potentially extragalactic origin. And halo stars are stars in the Milky Way's galactic halo, which are the oldest stars in the galaxy and the most metal-poor stars in the galaxy. So they're a relic of the early universe. And they didn't form in the disk. Instead, they are believed to have formed in the proto-galaxies that initially came together to form the Milky Way, and in the gravitational interactions of that process, the early generations of metal-poor stars were scattered out into a halo around the galaxy, before the disk was even properly formed. And because they're so far out, and because they came in during the formation process, some of these stars could be of extragalactic origin. in addition to the formation process, they could be from satellite galaxies that collided with the Milky Way after the disk formed, or they could even have been pulled away from other galaxies like maybe Andromeda or the Magellanic Clouds by tidal interactions. And they're not just around the galaxy, they have these looping orbits, which means they pass through the disk, so we can see a few halo stars in the disk. And this study looked at those stars to see if they could find any planets. Or rather, they did simulations of how difficult it would be to find planets around these stars given their lower population. And this here is a graph not of the occurrence rate, but of the completeness rate, which is the probability that if there's a planet there, we would be able to detect it. And the completion rate is not great. Because there are so few of these halo stars, even the easiest to spot planets, the hot Jupiters, only have about a 44% chance of being detected, but that's still high enough to do statistical studies. And what they found is, when they looked at actual halo stars, they did not find any planets. And combining that together with the function of completeness rate, they calculated upper bounds for the number of planets in each of these categories. And those upper bounds are pretty low. For hot Jupiters, they got 0.52% as an upper bound, whereas for disk stars, the number of them with hot Jupiters is more like 1%. And they couldn't really get down to Earth-sized planets or even super-Earth-sized planets just because detectability is so low. But they did detect lower bounds that indicate significantly fewer halo stars have planets than disk stars. And this is what we expect, because these halo stars are much lower metallicity, they have fewer solids in them and around them to form planets. And in fact, theory predicts halo stars should have 10 times fewer planets than disk stars. So, this study is one that actually shows what we predicted to see. Next, we had a couple interesting studies about characterizing exoplanets. This is looking at the atmospheres to see what they're made of. This is my field of expertise, so I certainly found it interesting. And it's also what JWST will be focusing on in many of its studies of exoplanets. So the first one was in-depth direct imaging and spectroscopic characterization of the young solar system analog HD 95086. And this isn't that remarkable by itself. We found directly imaged planets before, and many of them are similar to this one. This is a young A-type star, more massive than the Sun, and it has a super Jupiter-type planet, about 4 or 5 Jupiter masses, in a wide orbit. We found systems like this before, but this one is unusual in that it is so young. It's only 13 million years old. The famous HR 8799 system, which has 4 directly imaged planets, is 30 million years old, which is still pretty young, but 13 million is so young that there are still debris belts around the star, which means that other planets, especially rocky planets, may still be forming there. And this study was able to get a spectrum of this planet. It's a spectral type L6, which is a classification usually used for brown dwarfs, but it works just as well for young, hot planets. And this is an emission spectrum, so it's looking at emitted infrared light rather than starlight passing through the atmosphere, since obviously it doesn't transit. And there aren't a lot of data points here, but for a directly imaged planet, this is a decent start. And it's enough to fit a spectrum. And they fit spectra from a couple of different model sets. And it's not really conclusive yet. There's quite a wide range of possible temperatures in these spectra. But it's a good start, and definitely worth following up on in the future. Here's a paper that looks at planetary atmospheres more broadly. A temperature trend for clouds and hazes in exoplanet atmospheres. And this does apply to transiting planets. Because with transiting planets, you look at light passing through the planet's atmosphere when it goes in front of the star. But because it's edge on, there's a lot more air in the way. So if there are almost any clouds at all, it'll just completely block the starlight. And this is a problem that we've had especially for low-mass planets. The clouds just completely block everything out. That's one of the reasons why we need JWST, because it can look at longer wavelengths that will still go through the clouds. But in this case, this research group was looking at how the amount of clouds is affected by temperature. And it's a bit of a complicated question because there are multiple factors that can influence the formation of clouds, or more properly, aerosols. There are two main types of aerosols in a planet's atmosphere. One is traditional clouds, which are volatile chemicals like water or ammonia that condense into droplets in the atmosphere. This is what Earth clouds are made of. And there are also hazes, which are produced mainly by ultraviolet light reacting with carbon-bearing molecules in the atmosphere and creating this sooty material in very, very fine grains that can be lifted by the wind higher in the atmosphere. At least we think that's the main source of hazes. There could be others. Particles of sodium are suspected on some of the hotter planets. But the important thing is that hazes can occur at a much higher altitude than traditional clouds, and so they will affect the spectrum in different ways. And this first plot is measuring those cloud and haze altitudes for Jupiter. But this team was looking at a variety of exoplanets to see if they could see patterns in these cloud effects with temperature, and they did. There's a lot of spread, but there's a general trend, which interestingly does not really match theory. The trend they found shows fairly cloudy atmospheres at about 500 Kelvin, and this is consistent with what we see for super-Earths and sub-Neptunes, becoming more and more cloud-free up to about 1500 Kelvin, and then becoming cloudy again. And at those higher temperatures, the clouds are actually made of rock dust, or perhaps, depending on the temperature, maybe even droplets of molten lava, because it's that hot. But the odd thing is that we expect the cloud-free region, where the temperature conditions are just such that there aren't any common molecules that will condense there, we expect that to be down around 1000 Kelvin rather than 1500. So it's not clear what's happening there, and these are still pretty rough statistics, so I'll be very interested to see what happens, especially with JWST, as we get more data to try to refine this plot a bit. There may be some new physics needed. And we have a paper about indirect characterization, prevalence of short-lived radioactive isotopes across exoplanetary systems inferred from polluted white dwarfs. And this is a pretty crazy method, where astronomers are looking at dead stars to understand planet formation. But it actually makes sense. You see, the logic is that planet formation is influenced by heat from short-lived radioactive isotopes, especially aluminum-26 and iron-60. And we know this happened because we can see it in our own solar system. But these isotopes are produced by supernovae, and because they're so short-lived, they won't occur naturally in the molecular clouds that form stars. They have to be seeded there by a nearby supernova not too long before the star forms. And, of course, that will happen fairly often because stars form in clusters, and the most massive stars will produce these supernovae before the less massive stars, which form slower, are even able to form. But they're still not going to be evenly distributed. So that's one of the major unknowns in planet formation, because there can be a range of the amounts of these radioisotopes. But because these isotopes are solids, they decay to magnesium and nickel, which are major components of solid planets. How do we measure them? We can't exactly see them in the atmospheres. Well, it turns out we can see them in the atmospheres of their stars after they die. I've talked in previous episodes about polluted white dwarfs, where asteroids or chunks of planets, or perhaps moons, fall into the white dwarf after the star dies, and thus seeding its atmosphere with the solid elements that compose the planets. And by observing these polluted white dwarfs, we can measure the compositions of the rocky planets that they used to host billions of years ago. And this is really just a theory paper. They were talking about the modeling process and didn't really analyze any white dwarfs directly, but it's a really clever method, and I'm excited to see what they turn up when they start to apply it to real stars. So stay tuned for that. Next up, we have a couple of papers about planet formation. First, the growth and migration of massive planets under the influence of external photoevaporation. And I've talked about photoevaporation a few times before. This is where ultraviolet light from the star blows away gas from a forming planet or from the protoplanetary disk itself. And this can have significant effects on sub-Neptunes. It's one of the major processes that's believed to evaporate the atmospheres of sub-Neptunes, but it can also affect giant planets despite their much larger gravity. Because even though an established giant planet like Jupiter will be pretty resistant to this photoevaporation, the gas disk that it forms from is not. And if there's enough ultraviolet flux, that gas will be eroded away before the planet can grow to large sizes. And that's exactly what this team modeled in computer simulations. They ran simulations of planets forming at different distances with different ultraviolet fluxes. And they found that a higher ultraviolet flux leads to a lower final mass. This is relative to the Sun on the y-axis. And for very high ultraviolet fluxes, that says 10 Earth masses, that's a bare core. It's not able to accrete any gas from the disk. And it also affects migration. Giant planets migrate inward after they form, but that's in large part due to interactions with the disk. So if the disk evaporates faster under a higher UV flux, there won't be as much migration. And under the highest UV fluxes, the planets don't migrate at all. Low UV fluxes, they migrate in very far, and some of those white areas may involve falling into the star, although that's not a guarantee. We're still not exactly sure how often that happens. But migration is an interesting problem in its own right. And there was another paper last month looking at a more detailed treatment of giant planet migration that says maybe it doesn't quite work like we thought, always pushing the planets into the star. And the basic idea here is that, as I said, giant planets migrate due to tidal interactions with the disk. And if you do an idealized theory calculation, you can calculate that the main result of this migration is that gas in the disk is sort of slingshotted outward, and the exchange of angular momentum causes the planet to gradually drift inward. Or if the gas is thick enough and is still accreting onto the star, it'll just kind of drag the planet with it as it's pulled into the star. But also, because the planet is accreting gas, it'll open up a gap in the disk where it swept all the gas out of the way. And it's the exact shape of these gaps and their interaction with the planet that affects the migration rate. And in the computer simulations, this team found that sometimes the migration can go in the opposite direction, away from the star. And in fact, they found that for a significant range of parameters, planets will pile up at Jupiter-like distances. And in this plot, it's exactly 5 AU, but it's generally more like a few AU. Planets farther from the star will drift inward and stall at around Jupiter distances, and planets formed closer can migrate into the star, but they also might migrate outward and stall at Jupiter-like distances. And we think this may even be true of Jupiter itself, sort of. We think that Jupiter formed where it is now, or maybe a little closer, then migrated inward quite a ways, maybe as close as 2 AU, twice Earth's distance from the Sun, and then migrated back out to where it is now at 5 AU. And in large part, this is due to interactions with Saturn, so that's a whole other complication to the theory. But it does paint a picture that migration is a little more complicated than we thought. Next up, we have a couple of papers about the architectures of planetary systems. The first one is about the peas in a pod model, which is where compact planetary systems, like the ones discovered by Kepler, tend to have planets that are similar in size to each other and spaced evenly in logarithmic distance from the star. And this is something that's been getting a lot of attention the past few years. I've talked about it before. And in fact, I saw a pretty major paper on it just a couple days ago, so look for that in next month's review. But this is an interesting paper that took a very different approach to the idea. It's kind of off the wall, but it makes a weird amount of sense. Generalized peas in a pod, extending intrasystem mass uniformity to non-TTV systems via the Gini index. And non-TTV is transit timing variations, which is sort of the quick and dirty way to measure planetary masses without taking detailed radial velocity observations. But the interesting thing is that they use the Gini index. because the Gini index is not an astrophysical term. In fact, it's an economic term. It's a popular measure of economic inequality within a country or population. A Gini index of 0 means everything is completely equal, everyone has the same amount of money. And a Gini index of 1 is the most unequal, where one person owns everything. And in real-world countries, the Gini index ranges from about 0.25 to 0.63. That's not that important. The important thing is that you can apply it to mass of exoplanets. A Gini index of 0 means the exoplanets are all the same size. A Gini index of 1 means that one planet is much larger than all the others. And I really like this interdisciplinary stuff because it actually does work. It gives us a quantitative measure of how strong this peas in a pod relation is compared with a random population. And that's exactly what Goyal and Wang did here. They took 17 planetary systems, calculated the Gini index for each one, and then added them up. They could have taken an average, that might have been more intuitive, but they added them up, and then they mixed up all the planets and calculated it again, and did it a bunch of times. And you can see that the actual Gini index, which ranges from 0 to 0.4, so on average more equal than countries on Earth, I guess, the real Gini index is quite a bit lower than it would be for a random sample. So this is one more measure that the peas in a pod phenomenon really is real. But note that this applies only to compact super-Earth systems. Other systems, like our own solar system that have more spread out rocky planets, don't follow this pattern, and in fact, in our solar system, the rocky inner planets have a fairly unequal Gini index of 0.6. This is another paper looking at these compact planetary systems, stable lifetime of compact evenly spaced planetary systems with non-equal masses. And this is looking at the gravitational stability of pairs of planets in these compact systems. And where it says non-equal masses, we are aware of a few systems where the masses are very different, like a gas giant next to a super-Earth. But they're actually talking about small differences in mass. So this is directly addressing the peas in a pod phenomenon, and looking if planets that are exactly equal in mass are more stable than planets that are a little bit different. And to figure this out, they created a computer model of two planets in nearby orbits with different masses, and integrated them over time to see how stable they were. So here's one example. In this plot, the period ratio runs from 1.068 to 1.142, which is equivalent to 3.5 to 7 mutual Hill radii. The Hill radius is the distance from the planet at which the planet's gravity is stronger than the star's gravity. So it's sort of a sphere of gravitational influence. But to be stable, it's generally accepted that distances need to be a factor of 5 larger than the Hill radius. And in fact, in this case, that's not enough. You need 7 Hill radii or more to have stable orbits. The vertical axis is how long before the first close encounter between the planets, which would significantly distort their orbits, not kick them out of the system yet, but it would only take a few such encounters to do so. And note that the time is in orbits, not in years, so a short period planet, it would be a lot faster. And even at 7 mutual Hill radii apart, the planet's orbits are only stable for 1 million orbits. And this is interesting because 1.142 is, I'm not sure if it's still the smallest, but for a long time it was the smallest period ratio we had seen in a planetary system. That's a 7 to 6 period ratio. So we have seen a couple of planets that are that close, but it doesn't look like that's a stable system. And if you want more stable ones, they did this one plot that goes all the way out to 10 mutual Hill radii, which does appear to be stable for billions of years. But the important thing is looking at pairs of planets that differ in mass by different amounts. And note that these are absolute differences in mass, not fractional. And for super-Earths, we're talking probably 10% or less difference. But they look at differences between 1/100th of an Earth mass and 0.3 Earth masses, and they find that it doesn't actually affect the stability that much. For 1/100th of an Earth mass, difference. There are these weird wiggles in the plot, and those are orbital resonances that are stronger and more precise if the planets are exactly equal. But as you go to a larger difference in mass, all it does is smear out those resonances. It doesn't really affect the stability. Of course, the other possibility for even more closely packed planetary systems are Trojan planets. And the Trojan points are the L4 and L5 Lagrange points that are 60 degrees ahead and behind a planet in its orbit. They're named for the Trojan asteroids, which occupy these points for Jupiter. Jupiter has a lot of Trojan asteroids. The other planets have a few to none. Earth has a couple, Neptune has a few, I think Mars has a couple, and the others are just really not stable. But these are points where, if there aren't too many other gravitational disruptions in the system, objects can orbit stably ahead and behind a planet in its orbit. And in fact, there are other types of orbits, like a horseshoe orbit, where instead of staying in one Trojan point, an object will drift back and forth between the two of them around the far side of the orbit. And there are a couple other possibilities as well. But the important thing is, these points are stable if the star's mass and the planet's mass are sufficiently different. This is assuming that the object in the Trojan point is small and of negligible mass, and that would be fine if it's, say, Earth versus Jupiter. But the Jupiter, or Jupiter analog, needs to be significantly smaller than the star. And in our solar system, Jupiter works just fine for the Trojan points, but not so well for the horseshoe orbits. You need something a little smaller, like Saturn, for the horseshoe orbits to work. But the trouble with this is the L4 and L5 Trojan points are energy maxima. A Trojan planet would not be at the bottom of a potential well, it would be at the top of a hill. And it stays there because of conservation of energy. But if it loses energy somehow, it could drift away from the hill and fall out of the Trojan point. And how could that happen? Tidal interactions. The sun causes tides on Earth, not just the moon. And those tides could cause the planet to lose energy. And in fact, Dobrovolskis and Lissauer did simulations of Trojan planets with tidal interactions, and they found that these Trojan points are unstable on a timescale of about 1 million years. So sadly, this suggests that there probably are not going to be Trojan planets out there in the galaxy. Not so fun for science fiction, but still a very interesting result. Meanwhile, we do have a couple papers addressing issues of habitability. The first one is one more reason why we have to be careful when we declare planets potentially habitable: the role of atmospheric exchange in false positive biosignature detection. This is a bit of a weird case because it requires potential biosignatures to exist on another planet in the same system, but potential biosignatures can still come from non-biological sources if conditions are right. It's when they get transferred to another planet with different conditions that they can look like actual biosignatures. And the theory here is that if atmospheric gases escape from a planet or are perhaps ejected by impacts, they could be accreted onto another planet in the same system. And in fact, this happens with the moons of Saturn, where water ejected by cryovolcanoes on Enceladus gets split into hydrogen and oxygen when exposed to UV light from the sun, and the oxygen drifts through space and some of it accretes onto Titan. And this could certainly happen, especially in close-packed exoplanet systems. And this is important not just because it would transfer oxygen from one planet to another, perhaps from a non-life-bearing water world or ice world to a rocky planet that looks potentially habitable based on its size and temperature. It's not just that the oxygen would be transferred from one planet to the other, it's that it would build up in the upper atmosphere of that second planet. And as I discussed earlier with transit spectroscopy, anything that shows up in the upper atmosphere will show through that much more clearly in a transit spectrum. Because with that grazing angle, any small change, especially high up where the air is very thin, will have a large effect on the spectrum. And when this team simulated transfer of water and oxygen from TRAPPIST-1d to TRAPPIST-1e, two planets in the potentially habitable zone of one of these compact systems, they calculated that enough oxygen could build up in the atmosphere of TRAPPIST-1e to be mistaken for a biosignature. So it's important not just to characterize the one planet, which JWST will be doing. It's something that's coming up fairly soon. It's important to characterize the entire system, and luckily JWST will be doing that for the entire TRAPPIST-1 system. But it's important to look at the system as a whole. Now, for something a bit more speculative, here's a paper looking at potentially habitable conditions on planets with hydrogen atmospheres. These could be sub-Neptunes or super-Earths, because planets with a small enough amount of hydrogen will still have a solid surface under that hydrogen, but that's expected to be pretty rare. But it could even apply to true sub-Neptunes that have a thick hydrogen atmosphere and may not have a solid surface. The rocky surface and liquid hydrogen under the atmosphere could just dissolve into each other. But this model suggests that might not necessarily happen because there could be a distinct layer of liquid water between the solid core and the liquid hydrogen envelope. And this is reasonable because ice giants like Uranus and Neptune are expected to be mostly water rather than mostly hydrogen. And they found that even for free-floating planets that don't even have a star, the interior could stay warm enough for that liquid water to exist at life-supporting temperatures. And for the right water fraction and hydrogen fraction, it could even persist for geologic times. So here are plots of temperature versus time with different masses of hydrogen in the atmosphere and different core masses. Not many, but you can see by implication that some of the curves do pass through the roughly 300 Kelvin temperature range where life can develop. And they built this grid of models, core mass versus envelope mass. This is something I've done in the past for very different reasons, and found that liquid water temperatures can persist for billions of years in this upper range where more than 0.1% of the planet's mass is hydrogen, and in fact typical super-Earths have about 1% hydrogen by mass, so that's right in the sweet spot. So there could be, potentially, life in these deep interior oceans of Neptunes and sub-Neptunes, and I'm not sure we would actually be able to detect it, but it's very interesting to think about, and to think about if there's ways to detect it. Finally, the most speculative papers, the ones dealing with actual aliens and if they're out there. The first one is sort of a reverse SETI situation, looking at how often Earth would be detectable by aliens, and specifically through microlensing. And I've talked about microlensing a couple times as well. It's what happens when a star and planet pass in front of a background star, and their gravity bends the background star's light around them to produce multiple images, making the background star appear brighter, and you can disentangle that light curve to measure the mass of the planet. And we do this by looking mainly at stars in the center of the galaxy where there are more of them, so they're more likely to line up. But it's a very rare event. Finding 10 planets by microlensing is a big deal. So the question is, how often would an alien civilization, perhaps one farther out in the galaxy, be able to detect Earth via microlensing? And this team computed the detection rate over the whole sky. And of course the rate is much higher in the disk, and in the Magellanic Clouds, and in those two other points, which I'm pretty sure are opposite the Magellanic Clouds. Because as long as you have stars in alignment in the right distribution, you can detect Earth from both directions. It's just like in the diagram above, you could reverse the direction in that picture with no problem. And what they found is most individual stars have a very low probability of detecting Earth, but there are a lot of stars. Any individual star will have a 1 in 1,000 chance per year at most, probably much less, of detecting Earth. But if you add up all the stars in the galaxy, Earth is potentially visible via microlensing from about 15 stars per year. So if there are aliens around enough stars, our planet may be detectable by them. And last of all, there's a new paper on the Fermi paradox, which is the famous paradox proposed by Enrico Fermi. If life is common in the universe, and so far there's little reason to think it's not, why haven't we seen any aliens? And this paper looked at potential astrophysical reasons why alien civilizations might not survive as long as we think. So they looked at the usual processes of self-destruction and outward colonization, but they also looked at astrophysical phenomena that could destroy an alien civilization, like supernovae and gamma ray bursts, or even an active galactic nucleus, if something big falls into this black hole in the center of the galaxy. And they found that these astrophysical hazards could reduce the number of civilizations out there by a factor of 3. Remember, communication times are tens of thousands of years with most of the galaxy. So, an alien civilization needs to survive for tens of thousands of years to properly communicate with it, and of course, even to just detect it, the longer they live, the better. And if a significant number of civilizations can be wiped out by supernovae, that means there will be significantly fewer of them that we could detect. And in fact, in the early universe, when there were more massive stars, that factor of 3 is even larger. So that would explain part of the way why there are no very old civilizations that have already colonized the whole galaxy. Not all the way, but it's an important piece of the puzzle to solve the Fermi paradox. So, still no aliens, but at least we can expect a lot of interesting new exoplanet science in the coming months.